All right, let's start. Okay, so yeah, can you see the screen? Is it visible for everyone? Okay. Yeah, I think Steve, you wanted me to go over this problem again, right? The last problem that we were doing. All right. Okay, so I'll quickly recall all of this thing that we did in this problem, and let me know if it's any better. Then, right? Okay. So, second, trying to open this chart as well. All right. So let's keep this chart over here. Okay. All right. So okay, let's begin. So we had a problem where we had a proton, right? And this proton is a positively charged particle, and it was standing still. So maybe it was stationary at some point, and then you release it, so it starts to move. Initially, its velocity is 0, and then it starts moving. And this is the graph that we have for the entire journey of this motion, that its potential difference varies with position as follows. So initially, its potential difference, its electric potential is maximum before it's released, and as soon as it's released, its electrical potential starts decreasing, and so on, right? So it's the journey is from this path A to B to C. The problem, first part of the problem, is to compute its velocity as it travels this trajectory from A towards C, right? Like this. So we make use of conservation of energy because we have to compute the velocity that contributes to the kinetic energy of the particle. And if we have for A to C, we have these values for electric potential. That means we have electrical potential energy as well. So we see that from A to C, what's happening? It is losing this electric potential, right? It's decreasing over here. And so what happens is all of this loss in electrical potential is being used into the motion of this charged particle, right? Because it's moving, it gains velocity as its electrical potential energy starts getting converted into kinetic energy. So from here we have this equation which says that the loss in electrical potential energy, which is minus change in potential times q, right? So we know from our work on even on gravitational fields, that the energy is given by the, so for example, if in electricity we deal with charges, the property charges, so we multiply this charge property with the potential, so we get energy, right? In gravitation or gravitational fields, it was the same, where we had the gravitational potential multiplied with the mass of the object was the gravitational potential energy. So in this way, this is the electrical potential energy, which is equal to half mv squared, that is the kinetic energy. U squared is 0, v squared minus u squared, as it's initially not moving, right? So we're left with this equation. Now, the change in potential from A to C. So we'll just see that what's the potential at A, it's 8. And similarly, we'll see the potential at C, which is 4. So the change in this potential is the potential at C minus the potential at A. And then you'll multiply, in place of Q, you'll put this in charge. For a positive charge, it's plus E. And half mv squared. M is the mass of this proton, which is the positive charge, and v squared is what we want to find. So we'll factor out this velocity squared expression, which comes out as this way from this expression. So this is the velocity if the proton travels from A to C. It will move with this velocity. Is the negative sign on the formula of EP part of the formula, or are we using it? No, it's actually, it's part of the formula, right? The potential energy is minus change in the electric potential dot Q, right? Loss is encountered in this change, right? So if delta, so for example, let me write this over here. If delta V is greater than 0, then what would be the case? And if delta V is less than 0, then what would be the case, right? So if it's delta V is greater than 0, that means it gained potential, right? Because the final potential is larger than the initial potential, means it gained potential. And if it is less than 0, then it's lost. It lost potential, because the final potential would be less than the initial value. That's why we have this thing. So is that clear, Alicia? All right. Okay. So that's first part of the problem. The second part of the problem is to figure out the maximum velocity of the positive charge when it was released from A. And then the other thing is to compute the same maximum velocity if it was released instead from C. Meaning that if this charge started its journey from this point A, then it will come down to B, right? And then this point B is where it has the minimum potential. So that's its most stable state that this charge can have. Because the universe works in this way that it minimizes things. Actually, I'm saying things, but there's a quantity, it's called action, but you don't have to get into that. But it minimizes this quantity, and that is the most stable state of the universe, of everything that we have. So even for this charge, the most stable state for this proton would be the minimum, to be sitting at the minimum potential. So as it starts its journey from A, it will come towards B, and it will eventually stop at B, right? Similarly is the case for C. If it starts its journey from C, it will go in this path. It might oscillate up and down like this, but it will eventually come to a stop at B at this point, right? Now, we want to compute its velocity, maximum velocity, when it is released from A. So first we start doing that. So we see that if it's released from A, its initial potential is 8, and it will eventually come to a stop at B. So its final potential is 1. Everything else remains the same. So we have that the loss in electrical potential energy, because it was standing at this point where it had more potential. So it had more potential energy, and it came to a lower potential, meaning that it lost electrical potential energy. And as it did that, it converted that electrical potential energy into its motion, meaning its kinetic energy. So that was the kinetic energy gain coming from this loss in electrical potential energy. Which means that now I'll use the same expression, minus delta V times Q is equal to half mv squared. where delta V is the change in potential, which will now be the potential at B, which is the final potential that it can be at, this one, point B, and initial potential is at A because it's starting its journey from A. So we'll do this thing, right? So minus, this is VB minus VA times Q, and the rest is just putting in the values, right, to solve it for velocity. And this gives you this equation, and now just put in the values in this equation and you'll get velocity squared, and then square root it to get velocity, right? Now, the final thing is to say, compute this same thing if it was instead released from this point C, right? So if it was released from C, it will do the same thing. It will come down. It might oscillate like this back and forth in this way, like this, like this, like this, but it will eventually sit at this point B. Now, the final potential is still 1, which is at VB. Initial potential is now at the potential at C. So our equation becomes this thing. Change in potential, which is minus del V times Q. So VB minus VC, final is VB, initial is VC, times Q is equal to half mv squared as so. And this gives you the expression for velocity as this thing, velocity squared, and you square root this thing to get velocity. So that was the solution to the problem. Any thing that is unclear or any doubt? Is it clear now, Hasib? All right. Okay. So is it clear for everyone? Everyone understands it? These constants, the value for this Q and mass of the proton is always given in the question, right? So that was the problem. All right. Okay, perfect. So with this, now let's start our topic of capacitance, right? So let me just rearrange this thing. All right, so let's go to the next page and begin our study of capacitors. Okay, so capacitors are really interesting devices. Suppose that if you wanted to, we have, how many pending chapters are pending for us? All right, so we have this electricity and magnetism. We'll finish, we're doing capacitance right now, then we'll do magnetism as well. So after that, we'll talk about electromagnetic induction, and where we'll talk about alternating currents. So this whole chapter of electricity and magnetism is quite big. So we'll try to get it done as quickly as possible, but as efficiently as possible as well. And then we start our topic of quantum physics, where we'll talk about, what do you call that? Mainly we'll focus on I forgot the name of this effect where you shine light on a material and it throws electrons, a photoelectric effect, right? Photoelectric effect and nuclear physics. So I cannot, at this moment, I cannot list down the number of chapters, but after the class, I'll let you know in the group, right? Asit, is that okay? All right. So, okay. So now let's begin the study of capacitors. Suppose that you want to store a charge. For example, we have talked about charges. We know charges very well now. By now, we have these two different types of charges, positive and negative. Suppose that you want to store all these charges in some place. That's why we construct a device using the laws of physics, which is known as a capacitor. It's essentially an electronic device that is used to store charges. And that from those, because it's storing charges, it is essentially storing energy, right? So a capacitor is an electronic device, right, which is used to store charges. If I'm saying store charges, that essentially implies that it is storing some form of energy. And we'll talk about this energy as well. Now, let's see how is a capacitor constructed, right? What happens is you have two plates. So I'll try to draw these two plates here. 1 second. So this is one of the plates, while here we have another plate, and these two plates are parallel to each other, right, as you can see. And these parallel plates have to be conducting. The plates themselves are conducting, right? So they can, if they are conducting, then only they will be able to store charges into them, right? So what happens is that they store charges because they're also separated. As you can see that there is some distance between these plates, right? I'm going to call this distance small d for now. And the plates themselves are conducting, but the area that is in between these plates is insulating, right? So the charges cannot flow into this area because we want to store the charges on these plates, right? So that's why the area between these plates, if I can highlight it, this area in between these plates is insulation, is insulating. Any material that is insulating, normally it can be air. It's the more common name for this is a dielectric medium, right? Which essentially you can say it's an insulator, right? It can be of different forms, air or some other dielectric material that is non-conducting, right? So, and these plates are conducting, so these will store charges. So for example, if this plate stored positive charges, then the opposite plate, the plate that is opposite to it, will store negative charges. So what happens is, if I take this device, right, and I connect it to a battery, for example. So I'm going to do this now. I'll take a battery. So this is my battery. So this is the positive, this is the negative terminal of the battery. And let's connect this to a capacitor. You have to ignore these drawings because they're very awful. Okay, so this is one plate of the capacitor and this is the other parallel plate of the capacitor, and these are connected by this wire to a battery. What happens as soon as I do this, charges begin to flow, and when charges flow, you know, that's current, right? So current starts flowing into the circuit, right? So that means that if this plate had positive charges, then the positive charges will start flowing in this way. So I'll write it as plus Q. And they would start moving in this direction. They would come to this plate in this way. So plus Q is coming towards this plate. So what's happening is charge is flowing onto one plate and an equal charge is flowing to the other plate. Right? What I'm trying to say is, if you look at this thing, what is happening in this diagram, a plus Q is leaving this plate, right? This plate of the capacitor, and the other plate of the capacitor is gaining an equal amount of charge, right? So Now, suppose if I were to remove this battery, then there would be a net positive charge on one plate and a net negative charge on the other plate, right? Because, so suppose that I started with this, so this is the first thing. Second thing is, immediately I remove the battery. Now what happens, what is left on the capacitor? This capacitor is net negative charge. Why? Because one positive charge left this plate, and this plate gained that positive charge. So this plate will be net positively charged plate, right? Now let's, in now with this situation, the third scenario, or the third step for this thing is, let's take this now, this capacitor, which is net negative on the left and net positive on the, sorry, net negative on the right and net positive on the left. And let's connect this to something, to a bulb, for example, to see what will happen. So if I connect this to a bulb, I'm going to try to, or I'll just use the symbol, electrical symbol for bulb, which is X, I think, right? It's something like this. So this is a bulb. I connect this circuit to a bulb. What will happen? Can you tell me what, can anyone go ahead and tell me what would happen? So initially I had a capacitor that was both positively charged plates. I connected to the battery. What happened is, because battery has one negative terminal, from one of the plates, a positive charge started flowing. And from the other plate, that positive charge was gained by that plate. So one of the plate was left as net negative charged, and the other plate gained that charge. So now it's net positively charged. Then I removed the battery, and this was the situation. One plate was negative, one plate was positive. Finally, I take this capacitor and I connect it with wires to a bulb. Can you tell me what will happen? Will the bulb light up? Will the bulb not light up? And for how long? If it would light up, for how long do you think the bulb should light up? Can you unmute and anyone volunteer to suggest an answer for this thing? The circuit is closed, right? So what should happen? And the biggest hint is also that one of the plates is positive and the other one is negative. So there is a difference in, so what can happen? It should light up. Exactly, it will light up. And do you think it will light up for a small amount of time, or for it will light up all the time? I mean, what decides a continued period? Okay, so you say a continued period, as in, so it will stay lit for a long time, right? But think about this thing. There is only one net negative charge, because one charge left, right? So there's net negative over here, and there is a net positive over here. Why do we use batteries? Because batteries continuously supply charges from through the wires to our circuit. But capacitor just stored a small amount of charge, and then the battery was removed. So we charged the capacitor in this way, that one plate was net positive and one was net negative. So as soon as the charges flow off these plates, so what will happen is it will start to flow, in this direction. You can take any conventional, there are two different directions for currents. One you say is conventional, one you say is the other one. So if I say that the current is flowing from this negative to positive, then the charge will flow like this, and then it will again balance it out. And the charge would have been used up. Now there is no other supply that can give more charges, give a continuous supply of moving charges, because there's no battery in the circuit, right? So as soon as the charge flows off these plates, the bulb will again turn off, right? So the bulb will light up for a very small amount of time. And as soon as the charges flow off the plates of the capacitors, the bulb will dim and turn off, right? So is that clear? Is the idea of how capacitors work, how are they charged, and how can the charges that they store in them be used in a circuit? Is that clear? All right. Okay. So now with this, we can move on to the discussion of how much of a charge can a capacitor store in itself, right? Because here we saw that we stored a very small amount of charge, and it was not very useful, as the bulb only lit up for some amount of time and then it would turn off. I need to see how can I measure that, how much charge can I store in my capacitor. So how much charge can we store? That's the question that we need to answer. Okay, so the answer to this question depends on multiple things. One of the things it depends on is the type of capacitor, right? So what material capacitor am I using? So it depends on the, I'll just say, type of capacitor. It also depends on the dielectric medium that was in between the plates of the capacitor, right? So that means if it depends on these two things, right, it depends on the dielectric medium as well. This would mean that if this is my parallel plate capacitor, as so, the charge that it can store would depend on the potential difference between these two plates, right? So if this is, for example, positive and this is negative, there would be a net potential difference. I'll call it V, and it would depend on V, how much charge I can store. This means that the charge that I can store is directly proportional to the potential difference between these two plates. Now, capacitance comes from this thing, because when I write this thing as an equation, Q is equal to some constant multiplied by V. This constant turns out to be the capacitance. So this expression becomes Q is equal to CV. Right? And from this expression, you can define capacitance as C is equal to Q over V, which essentially is telling you that capacitance is just the charge stored in the plates, parallel conducting plates, per unit potential difference, right? So that's your capacitance. Q is the C is equal to Q over V. So that's how you define your capacitance. So using this expression, you can compute how much charge I can store in a capacitor. The more this value, the more the value for C, meaning the more charge I can store per unit potential difference, right? So as it is Q over V. Uh, Talking about the units for a capacitance, we know the units for charge are coulombs. The units for potential difference is voltage. And so if we combine these units as coulombs per voltage, right? So this is the units for capacitance. And we define a new name for coulombs per voltage as farads, right? So the unit of capacitance is farads, F-A-R-A-D, right? So in this way, we can also define a farad. As we saw that a farad from here is coulombs per voltage, right? So a farad, which is coulombs per voltage, which means that 1 farad is just the capacitance. Sorry, 1 farad is the capacitance of a conductor, right? That is at some potential, you can say unit potential when it carries a unit charge. So that's how 1 farad is defined, right? So 1 farad is the capacitance of a capacitor. That is at a unit potential having unit charge. Right. So with this, because I think we have less than 1 minute, uh, there are some problems that I want to do, and then we'll discuss capacitors in parallel and series arrangement. So I guess let's leave that for tomorrow, right? Because the meeting is going to end anyway. So let's continue from here in the next class. Right. Okay, so I'll end the meeting.